All right, folks. Hey there, Tuesday time. So that means you have a problem set. We're going to do the section 2-3 problem set today. So you had 2 days worth of lectures on that because there were seven theorems six theorems and then one postulate that was in section 2-3. So we're kind of just giving 1 day of problem sets after you had those two exit tickets the other day. Okay, so these are the problems I'm going to do. I'm going to do these ones, do these first three very quickly, then a little bit more slowly for the last three. So hopefully we'll get this done in less than 20 minutes. Just a reminder that you do have online, right? I'm putting up all the homeworks and whatnot. So even though it says in your Google Classroom what you should do today, you can always fall back on this too if you want to see this. And sometimes I show you stuff that's upcoming. Not doing this on Friday. We're not quite to chapter 3 yet. I thought maybe if we're going even faster than we've been going, we get to 3-1. But anyways, so make sure you do all these problems. Just want to remind you that the ones that I'm doing right now, this isn't your only homework, right? You got other problems to try. So spend about 40 minutes, split that between 25 minutes the asynchronous block, another 15 minutes for homework. Just knock it out, and then you'll be able to review the stuff in the Jamboard tomorrow and get feedback on things you maybe have not understood today. Okay, so about 40 minutes. Try to do all of them if you can. If not, right, try to do as many as possible, right? You just want to see as many as possible and then figure out how to do them when we review tomorrow on the Jamboard, or if you're able to ask questions here. All right, so starting out with these, I wanted to make sure you know how to do these because remember, geometry, a big thing you get out of the class is working with diagrams, right? Diving into diagrams, getting to know the diagrams, feeling more confident when we get something visually presented to us. We can kind of break it down. We can develop strategies. We can kind of see what's going on, look under the hood of the car, that kind of thing here. Okay, so questions 2, 8, and 10, all of looking under the hood of these diagrams. They're going to repeat it because, again, I'm going to be tracing over them. That's what I recommend in problems like this. Here, I don't even know what this problem's asking, but this is what I would do in a test right away. Measure of angle 2. Oh, I'm going to highlight angle 2. And I'm going to highlight angle 10. Oop, angle 10 is right here, and then I'll get back to that later. Anyway, we have that for angle 10. We have that for angle 2. Let's talk about that in a second here. So it says, use the given information to name the segments that must be parallel. If there are no such segments, write none. Okay, write none. All right, well, let's check it out here. We're trying to establish parallel lines. We have measure of angle 2 is equal to measure of angle 10. And are any of these lines parallel? Well, we can pretty much see pretty quickly, no, none of these are parallel. So how might they have been trying to trick us on this one here? Well, the way that I think they're trying to trick us here is that we actually technically do have a transversal that is forming the two angles here, right? This would actually be where you see the pink over the green. This would actually be the transversal. Okay, transversal right there. And then these would be the other two lines, right? Maybe we'll do the other two lines in black. So then we have RA, and we have UA, right? And we have UA. Because they share a point, they're obviously not parallel, right? They're obviously not parallel here. So believe it or not, 10 and 2 are actually same side interior angles. When two coplanar lines get cut by a transversal, well, on the same side in the interior of those two lines, right, we'd have the same side interior angles, the interior of the two lines and the same side of the transversal. So these are same side interior angles, but they don't have a special relationship at all. They're not supplementary. If they were supplementary, then those two lines would have to be parallel. But they're obviously not parallel because we see them intersect here. So for this, we would write none, okay, for no such segments, and we're good to go. All right, problem 2. So I'm going to be highlighting more of this stuff here, and maybe we'll talk about a shortcut on this one in a second. So we have here AU is parallel to OT. So we have AU parallel to OT. NT is parallel to OT. Boom. And boom, we found them, we drawn them. And here, I think we can deduce this, that AU and NT have to be parallel to each other. Because two lines that are each perpendicular, and do my perpendicular symbols a second ago, two lines in a plane, that is, too. These are planar figures, right? So I might write here in a plane. If you didn't have the drawing shown to you on a plane, right? A plane is a flat surface. If the drawing is not on a flat surface, then just reading this isn't enough to deduce that these two lines would have to be parallel, because potentially that they're skew lines. But anyways, these are all coplanar lines. So in a plane, we have all coplanar lines here. AU and NT are both perpendicular to the same line. They must be parallel to each other, right? These here, the 90 degrees here, 90 degrees here, these are corresponding angles, right? Corresponding angles that are congruent. They're 90 degrees each. So therefore, that would be enough to establish that the two lines are parallel to one another, the ones that are perpendicular to the same line. If we're just looking at this in the actual information here, say if we're just given this, we didn't actually even need this diagram right here to confirm that AU and NT were parallel, because, right, if we had just known this, that we're in a plane, right, we saw in our diagram we're in a plane, what do we notice here? Two lines, right? We have line 1 here is AU, and it's perpendicular to a second line, OT, and then OT is mentioned over here again. So line 1 is perpendicular to line 2, And we have a third line perpendicular to line 2, right, which is NT right here. So what we can deduce here is that in a plane, two lines, line 1 and line 3, that are each perpendicular to the same line, OT, must be perpendicular to each other. Must be perpendicular to each other. So this is line 1 and this is line 3. So remember that this is a theorem. Two lines that are each perpendicular to the same line, in a plane that is, right? In a plane, two lines that are each perpendicular to the same line are parallel to each other. I am confusing you guys there. Here. Remember, it turns to parallel. It's not perpendicular to each other. That's false, right? Totally. These are parallel lines here. Parallel, not perpendicular. So are parallel to each other. That's another reason why we don't call this the transitive property, right? Because we're dealing with statements of perpendicularness, and then it's going to become, we're going to establish something about parallelity. So this isn't the transitive property of being perpendicular to, because we have to do with parallel at the end here. So anyways, we avoid transitive in this section at all, like entirely, unless we're using something else, saying something else about equality or congruence in a proof. So anyways, there we go. We got AU, segment AU is parallel to segment NT, right? That's a way you can kind of break that down and maybe determine that. If you're not even looking at the diagram here. All right, number 10 here. So let's bust through number 10 right here. We're talking about measure of angle 2. Okay, angle 2 is right there. Angle 5 is right here. Okay, so what I'm noticing here is that these are unrelated angles, right? They're unrelated angles, but I'm going to mark them up for being at least congruent to one another, because maybe that'll help us later. These are unrelated because here we have one side, two sides, three sides, four sides. So of the two angles, there are four unique sides. They don't share a side, so they're not formed by a transversal. Remember, transversal would form angle pairs, where the transversal is the shared side between those two angles, and then you have two other sides there that will tell you like whether they're corresponding angles or same side interior angles and what have you. So this isn't going to tell us much yet, but perhaps, notice here they gave us a third angle that is equal, the measurements equal to the measurements of these other guys here. So let's mark that one up, and that's this one. Maybe I'll use a color that's a little bit different. Let's do yellow. You can see yellow. There we go. Right here, we got this one. And boom. So here, there's a transversal here between angle 8 and angle 2. So look at this. They share a transversal, right? Because the purple is over the yellow. And that means that these are on alternate sides of the transversal. So these are alternate interior angles. Okay, alt interior angles. Okay, so we can deduce here that, right, this is the transversal right here. These are alternate interior angles. And then the interior of the two lines here, RU has got to be parallel to AT. So that's what we get for this one, right? That information. So RU is parallel to AT. And it says here, given permission to name the segments that must be parallel. It looks like we might be able to come up with one more, because why would they talk about this? Why would they talk about measure angle 5? Maybe to distract us, right? They might be distracting us right here. But what you should be noticing here is that we have another transversal between, and does red and yellow make purple? Is that why Mr. Fortin just did that? I don't know. Does it? I think so. Red and yellow make purple. All right, transversal. Okay, red and yellow, those are primary colors, right? Make purple. I don't know. Anyways, there's the transversal, right? Right here, we have a shared side between angle 8 and angle 5. So that means that this line here, AU, okay, and AU must be parallel, okay, to NT. NT. There we go, right? Because we have a transversal here, and angle 5 and angle 8, right, are alternate interior angles formed by this transversal and these two lines here, AU and NT, the non-shared sides of those two different angles here, okay? So we get actually two angle pairs. There are two pairs, two line pairs, right? Two line pairs. Two pairs of line are parallel. So this pair is a line of parallel. Here's your first pair, and then this is your second pair of lines are parallel. So here, right, which segments, there could be more than one pair of segments that you could establish are parallel. So one pair of segments are parallel, another a pair of segments are parallel. Anyways, we only had one in this one. We have two pairs in that one. Hopefully that's not too confusing. All right, number 12 here. So I'm getting questions about this. I did this in the exit ticket. I gave you guys feedback on number 1 of the exit ticket. This was pretty similar. Normally, I spend more time on talking about existence and uniqueness. So it says here, describing existence and describing uniqueness. So this might feel kind of confusing. Why are we doing this? What does this mean? The idea is I really want you to understand why this phrase, exactly one appears in so many theorems because it's a very specific way of talking about things in scientific writing and mathematical writing. So in a normal year where we do have more time in class, we do have more time to get to more stuff, I'll spend maybe 20, 30 minutes talking about existence and uniqueness, right? The statements that establish that. And within that time, you get practice, you get examples, you get words to look for, look after. Okay. So I filmed that over the summer, actually. I filmed part of it, but it was 20, 25 minutes long. And I don't have time to show you that, right? I'm showing you enough stuff now. So, anyways, I'm hoping you can pick this up because in the book here, you're going to see this phrase exactly one, right? Exactly one in theorems. And what you say when you see exactly one, this is a statement of existence and uniqueness, okay? And uniqueness. So in this statement, through a point outside a line, there is exactly one line perpendicular to a given line. That means if we have a point outside of a line, we know that a perpendicular would have to, one, exist, because it says exactly one right here. There's exactly one that we can draw in. That means we must be able to draw one in. And there's only one, right? We must be able to draw one in. So there is a perpendicular through a point to a line, and there is only one, right? When you hear just the phrase only one, that means uniqueness. Doesn't necessarily mean it exists, right? Doesn't necessarily mean it's an existence statement. So when we hear only one, that refers to uniqueness. When we hear one, that refers to existence. That's the confusing thing here. So they put exactly one here because that means one and only one. Okay, so one way you could potentially reword this, guys, is through a point outside a line. Outside a line, there is one line perpendicular to the given line. All right. So this is a little bit confusing. We see the word one, but what this statement is actually saying, it's weird how you read scientific things sometimes. If they said, hey, there is one, that's just saying that there is a, or there is some, or it exists, right? So this is actually an existence statement here, okay? So they didn't say one. They didn't just say one only. They said exactly one, okay? So here, through a point outside a line, there is one line perpendicular to a given line. Okay, another way that I'm having you write that, which might be a little bit more clear to you in terms of establishing uniqueness, is, right, so there is one line perpendicular to a given line. You could say there is at least one, okay, at least one line perpendicular to a given line. That's a statement that establishes existence here, okay? So through a point outside a line, there is exactly one line perpendicular to a given line. So we know that there's going to be one, right? There's going to be one. And what's confusing here is that when you say in science and math, when you say there's going to be one, you actually aren't limiting yourself. You're just saying it exists, right? There's going to be one. So that's why you have to say exactly one to say there's going to be no more than one, because that would guarantee the uniqueness of that particular perpendicular. We can't draw more than one of those particular perpendiculars here. So statement 2 of this one here, you would say through a point outside a line, there is only one. Or you could say at most one, right? That's another way to sort of guarantee uniqueness of a particular feature, right? There is only one perpendicular to the given line. And that is a statement speaking to the uniqueness of that particular perpendicular. Through this point outside the line to the line, this point's kind of messy, and this is definitely doesn't look like a line that's perpendicular here. Okay, so exactly one, right? So the reason why our theorems, okay, a lot of theorems say through a point outside the line, there is exactly one line perpendicular to the given line, is because we want to communicate, right? It communicates both of these statements together, right? It communicates both uniqueness and existence, okay? It communicates both existence and uniqueness by saying exactly one. It just kind of removes any kind of the ambiguity about it or the confusingness about it when you're reading that thing. Okay, through a point outside the line, there is exactly one line perpendicular to the given line. Well, then I know there's going to be one. There's not going to be more than one, right? That's how I read it, right? As somebody who reads these math things and these science things here. If it had said just through a point outside the line, then there is one line perpendicular to a given line. Then you'd respond to the writer of that mathematical article or that science thing being like, you're being kind of vague there, right? You're just saying one exists, but like, what if there were two, right? Or what if there are three? Is that allowed? Well, then they'd be like, well, none, that's not allowed. So I should be writing that as saying exactly one, not just saying one, saying exactly one. Little confusing. If you're really confused by it, I can send you my 20-minute lesson on it. You can do it by yourself, but I don't want to spend that much time on this here. Just keep an eye on it. Keep an eye on for that phrase, exactly one. It'll be all of our textbook here. All right, number 16 here says find the values of x and y that make the red lines parallel. Okay, so we got to make the red lines parallel and the blue lines parallel. Okay, so if we assume, right, we got to get the blue lines parallel. We got to get the blue lines parallel, and we also got to get the red lines parallel. So now we need to start making some cases here about ways we can connect things. Sort of a puzzle problem that we have on something like this. Okay, so what do we see here? We have these are lines we're trying to get parallel. So we'd have to know, what do we have to know here? What do we got going on here? Well, here's maybe a transversal going on. So we know, oop, this is a transversal here. So here, if these were two parallel, we would know potentially this angle and this angle would have to equal each other, so that this would actually have to be x degrees as well here. Okay, x degrees as well. So what's interesting to me, I haven't done this one in a while. So I noticed this, for instance, I can add all these up, right? Well, the whole thing's a straight angle. So like if I added x degrees plus 105 degrees plus 2y degrees, what do I get? I get 180. So I'm just going to put that down. I don't know if that's going to be helpful for us, but I can at least set up an equation and equals 180. And I might simplify this a little bit. I might subtract the 105 from both sides because I think this might be a systems problem. For those of you in Algebra 1, you haven't really done systems too much yet. Don't really worry about it too much. I don't think I'm going to give you any system stuff on quizzes. Yeah, it's good practice for you guys who have done Algebra 1 so far. So anyways, that's a statement right there. X plus 2y has got to equal 75. And I just did that because these whole things have to add up to 180, right? All right, there we go, a straight angle. We add all the angles up. We got it. Subtract 105 on both sides. Boom, we got this. Let's see if we can come up with another argument. Maybe I'll shift my attention to the red here. I think I see it with the red here. All right, we got this 3x degrees. What do you think that connects to? Well, those aren't same side interior angles because, I mean, this is a transversal here. And so, well, these are same side interior angles, but they're definitely not supplementary. So anyways, what do we got here? All right, red. Well, maybe we'll extend the red lines. Maybe we'll see it a little bit more. We can extend the red here. Extend the red here. What do you guys see? Okay, so this is a transversal. I think I see it right here. Check it out. 3x and 105 degrees. Look at that. Those are alternate interior angles formed by what we're going to prove, like we're finding the degree measurements that are going to ensure that the two lines are parallel one. That's why this question is kind of confusing. Anyways, so yeah, these are alternate interior angles right here. So 3x degrees should equal 105. If it does, right? If this statement were true, 3x equals 105, those are two lines cut by a transversal and alternate interior angles are congruent, then that's going to be enough to prove that the red lines would have to be parallel to one another. All right, so it looks like here we can actually solve for x in this one here. 3 times x is 105, so we need to divide 3x by 3 to get what 1x would have to represent. Divide both sides by 3, we get x, and this is going to be 35, right? Because 3 times 30 is 90, and 3 times 5 is 15. 90 plus 15 is 105. There we go. So we got our x, and here we can go back and plug it back in to this other relationship that we have between x and y to determine what y must equal in this problem here. So I'm going to take this, and I'm going to pop 35 degrees in for x, and I'm going to solve for y. So subtract 35 from both sides. We get 2y equaling 40. Divide both sides by 2. Divide both sides by 2. And y is going to equal 20. All right, we got 20 degrees. We got 35 degrees. Good to go. I hope the group who's presenting that tomorrow watches this video because this is a tricky problem for some folks. So, it's kind of one of these ones where it's like, I can explain sometimes I think like maybe 40% of people will get it if they look really closely. If not, right, just look closely, try to get it, right? See what other people are seeing. That's the kind of exciting thing about, I think, geometry is that it's hard to see a lot of the stuff yourself. You can't see the color blue, right? If you don't know the word blue, it's very, very hard to see the color blue. That's why I always go back to that one. We have all these words in geometry. If you don't learn them, right, if you don't learn the definitions, it's gonna be hard to categorize and organize your brain to know what to do with a lot of stuff. So again, getting used to diagrams is really an important thing, right? So organize your brain, definition, postulate, theorem, right? Organize it that way, and then something like this becomes a little bit easier. And seeing examples is really helpful for that. Okay, we have a proof here. So remember, with any proof, you need 4 things. You need to draw out the diagram. You need to write the given and proof statements, and finally, statements and reasons. For the sake of time, I'm not going to spend the time. It takes a minute. That's it, right? A minute each proof. Copy down the diagram, write the given and proof statements. But I'm going to talk you through it because copying down the diagram and writing the given and proof statements are actually a really good way to think about what you need to say. I'm copying this down. Ooh, I got 1, 2, 3 angles. These look like alternate interior angles, right? So as you're copying it down, you're making observations. These aren't really related. I don't know. This is, oh, these would be corresponding angles right here. Angle EBA and angle C, right? You're talking about things in your head. If you don't write it down, you're not going to be able to think about it, right? You're not going to be able to approach it that way. So that's why definitely, right, in addition to be a required part of writing a proof, you really got to do this because if you don't draw down the diagrams, then you're not thinking about it. You're not giving yourself a chance, right? As good of a chance as other people are who are spending a minute to write it down, okay? So anyways, just some observations here, right? These are corresponding angles. These are alternate interior angles. Those might come in handy. It looks like these might be perpendicular. And if we look to our given statements here, let's maybe start with these, and we'll mark it up, right? So to help us here. Ooh, I see segment DA mentioned, okay? Segment DH mentioned. So that's right here. And this is the same segment is perpendicular to 2 other segments in the same plane. So in a plane, we have BE, which is right here, is perpendicular to DA, and CD is perpendicular to DA. So I think we're probably going to use the theorem in a plane. 2 lines that are each perpendicular to the same line are parallel to each other. That's my guess, is that that's going to come up at some point in time. Is that we're going to prove CD and B or E are parallel, and that's going to help us. Our goal here, now let's work backwards here. What's our goal? Our goal is to say that angle 1 and angle 2 are congruent, and I'll do that. I'll put a question mark. We're going to work towards that, and I think we can do that, right? If that line is parallel to that line, why does angle 1 and angle 2, why must they be congruent? I hope you know, right? But we'll still do the proof together so that we can get it here. All right, step 1, write down your givens, right? We got to list it down as our given premise because we know once we've stated that these 2 segments are perpendicular to the same segment, we know we're in a plane too, right? The given diagram showing us this is a planar figure. So we don't need to mention that actually in the proof. But what we can do is to say that BE is parallel to CD because we've stated this in step 1, 2 lines that are each perpendicular to the same line, and then in the given diagram, that's the in a plane part. These are all coplanar. So we now know that we have in a plane 2 lines that are each perpendicular to the same line are. Okay, so now that we've said this, we can make a conclusion here. So that's why you have to say this, right? You have to say this as step 1 so that you can use this theorem, right? And everything that comes at the beginning of a theorem, right? It's something to look after for too with theorems. At the beginning of the theorem, kind of after the if statement or the thing that's given to you here, you need to say that in the proof before you can get to the conclusion of what that theorem says. So the conclusion of this theorem is, after we have in a plane 2 lines that are each perpendicular to the same line are, the conclusion is parallel to each other, right? That's why we wanted to break this theorem out so that we can say this, right? We can say BE and CD are parallel to one another. All right, step 3. Wow, this is just a 3-step proof right here. Now that we got CD parallel to BE, and we have a transversal here, BD, helping us form angle 1, angle 2. So here, I'm going to extend it a little bit here just to make sure we see the lines a little bit more clearly. This is our transversal. Check it out. There's our transversal right there. So that means that angle 1 and angle 2 are congruent. Why? Well, they are alternate interior angles formed by parallel lines in a transversal. So we need to work that out and get that into our proof. Angle 1 congruent to angle 2. Why? Step 3 would be if two parallel lines, right? In step 2, we established that we had lines that were parallel. So two parallel lines that are cut. If two parallel lines are cut, so no need of that, are cut by a transversal, then alternate interior angles are congruent. And there you have it, just a 3-step proof right there. Had I known that this was going to be a 3-step proof, I would have given you number 22 as well, so I could give you guys another proof, because I think I only give you one proof from this one. Lame, boring. We want to practice more of these proofs here. I know you guys, you're just like, no proofs, too many proofs, too much work. That wasn't too bad right there. We got that one done. This was more work, honestly. Like, this is more work here. And this might have been more work too. All right, so there we have it. There's 6 problems that I did for you guys right there. Email me if you have any questions. We'll go over to the Jamboard tomorrow and then keep on chugging, right? Let's turn the page, right? You just want to see as much stuff as possible. Again, this year's not about perfection. It's about just getting into diagrams, figuring it out, trying to do as best as we can do. Have a great day, guys. I'm going to send your quiz grades out later today. All right? Enjoy that. See you later.